very delighted to introduce Dan Gillick to you. Dan is one of the original and one of the most appreciated instructors in our Masters of Information and Data Science program, about which I will say something more later, but I'll give you a bit of his background. He graduated with a BA from Wesleyan University, and this tells you a lot about Dan. He double majored in computer science and English literature. And then he came to Berkeley to do his PhD in computer science, where I guess he didn't do much English literature. He has been working at Google ever since he finished graduate school, working mostly on natural language processing, which, as many of you probably have noticed, has kind of exploded over the past couple of years. I've heard Dan say that when he started at Google, there was a small group of them doing NLP, and now it is how many? Hundreds, thousands of engineers in the field. One thing that you don't know about Dan, maybe, except for him probably, is that he has won both national and world championships playing, fill in the blank, Ultimate Frisbee. Very cool, very cool. He's on his way to New Zealand, and we're really delighted that we got a little bit of time from him today. I just wanted to say that he's an incredibly gifted instructor and speaker, so you're lucky to be able to hear from him today about the work he's doing. He built a course on machine learning. There are sort of applied machine learning class. He also built a course on natural language processing, and then we added in I think a bow to the students, NLP with deep learning, because everybody wanted deep learning classes. Both of them are incredibly popular classes, and so I think you're should be ready for a treat now. I'll hand it over to you, Dan.
Okay. It's green. All right. Anyway, nice to be here. Nice to see some familiar people, so that's good. Okay, so I've never really given a talk quite like this before. This is sort of, doesn't represent any particular paper that I've worked on. It's just some stuff that I'm working on at Google over the last 6 months or so, and I think it's interesting. And so I'll try to sort of present it to you in a way that I think hopefully is high level enough that you can get the general idea, and with a little bit of technical detail, but it's a little hard to sort of trade off technical detail and sort of high-level overview, and I'm not quite sure what everyone's backgrounds are, so I'll give it a shot. Okay. Oops. Okay. So here's a screenshot from Quora, which is this website that you go to and ask questions. This particular question, I guess Quora thinks is of interest to me, but anyway, so here I've typed in a question which is of interest to me. How does Blue Bottle cook their eggs? Something that I've actually wondered about for quite some time, Blue Bottle being just down the street from my house. I've always been impressed by how they cook their eggs. And if I type this into Quora, you'll see that it suggests a bunch of possibly related questions that maybe I do care about. Like, where does Blue Bottle get their glass coffee mugs from? No, actually, that's not really that related. How do IHOP and Denny's cook their eggs? Nope, definitely not related, and so on. Down at the bottom, we've got, how do blue-tongue lizards lay their eggs? Yeah, that's pretty far from what I'm interested in. But anyway, they have this search feature where you type in a question and they search their database, and maybe you'll find the answer to something that that's related enough that it will satisfy you. Okay. And so this is the problem of similar question retrieval. So at Quora, they have something like 10 million questions with answers. Maybe it's more by now. So people are typing in questions all the time. Other people are coming along, experts in various categories or non-experts, and answering questions. And the problem that I'm interested in, at least for this talk, is given a new question, can we retrieve the closest matches? Right? So how do I pull this sort of needle out of a haystack, given the sort of question I have, to find the relevant question that may be out there. Relatedly, how do we score the similarity between two questions? Okay, so you can see how those might be related. By the way, Google has the same problem, although at a somewhat different scale. So you may have tried typing, just instead of going to Quora, you can type a question into Google. And sometimes you get sort of a direct answer like this. Type in how to poach an egg. By the way, all my examples have to do with poaching eggs, so I'm sorry. And then in this particular case, Google has pulled out this little like recipe from this BBC site. Sorry, bbcgoodfood.com. Probably not related to BBC. And so they have the same problem, right? Google knows about probably an order of magnitude more questions and answers that they know are pretty good from the user logs and so on. And given some new question that might be phrased a little bit differently, they want to know, like, well, can we find an answer to your question, even though we don't have that exact phrasing in our database? And actually, this is like this kind of retrieval problem appears all over the place. Like, lots of companies have frequently asked questions sites, and people are always asking them the same questions, and they want to know, like, how can they route new questions that they get to like their database of questions that have known answers, right? So this kind of problem comes up a lot. And actually, it's a specific case of search, right? It's a specific case where the input is a question and the output is a question. But there's all kinds of other search problems. So just to give you a few examples, like the standard web search is you type in a query and you're looking for a document. Well, one that Google's interested in is typing in a query and you're looking for an ad. Usually you're not, but Google wants to find a relevant ad for you. Maybe you type in a query and you want an image. So there the modality is different, right? Like you have to compare queries and images. Or maybe you type in a query and you're looking for a video. Or even something sort of the reverse, where you have an image, like you take a picture with your camera, and Google would like to show you a document that's most relevant, right? So I take a picture of like this egg dish that I'm eating, and Google says, oh, that looks like the eggs that they serve at Blue Bottle or whatever. Okay, so really this is a talk about search. And I'm going to talk about this. I'll use as a lot of examples as sort of question-to-question case, because I think it's sort of simple enough that it's sort of easier to discuss. By the way, like, please interrupt and ask questions if stuff I'm saying is confusing. Okay, so first of all, classical retrieval systems, well, they date back further than the 90s, but the basic ideas are essentially unchanged since search engines were created. The key idea is the inverted index. Right? So if you want to find documents or maybe a question that's relevant to the question you just asked, you should keep track of this inverted index so that you can take each word in the question and look up all the places where that word appears really quickly. Right? And here's a little schematic of what an inverted index construction kind of looks like. On the left you have terms, on the right you have the items that you're indexing. So like items 1, 2, and 3 all contain the word blue. Item 1 contains the word where, and so on. So you're probably all familiar with this kind of thing. So the way search typically works is you have this inverted index that you've created from all your data. Then given some query, you retrieve some candidates, and then you re-rank them. So you sort them based on whatever criteria you might have to show people. When Quora was showing you the top questions that they think is relevant, they use some inverted index to find other questions that had lots of similar words, and then they did some ranking, and I'm not sure how the ranking works. Okay, so that's sort of classical retrieval. The shortcomings are that recall is limited by this word overlap, right? So in my case, I was looking for something very specific about poached eggs at Blue Bottle, and maybe there's a question out there in Quora which is relevant, but we weren't able to find it, and maybe it was because we were limited by this word overlap thing, right? The other shortcoming is we can't use the inverted index directly to retrieve across modalities. Like if I wanted to retrieve images, there would be no way to directly use an inverted index. So often people do this sort of trick where you try to annotate images or videos with words, and then you use that to construct the inverted index, right? but it's, you could miss a lot that way. Okay, so what I want to talk about is not classical retrieval, but sort of a new idea, which has to do with neural networks. And I'm going to call it continuous retrieval. And there's a few pieces, and I'll try to talk about each of the pieces. Okay, so the first piece is, you'll see they all involve some kind of learning, whereas classical search, or the inverted index, doesn't really involve any learning. So the first piece is, let's learn to represent objects as continuous vectors. Okay? So we want to come up with some framework, some kind of model that can take arbitrary objects, text or images or videos or sound, and represent them as vectors in some continuous space. Right? So here's an example of two-dimensional space. And you could imagine my model might place this object, how to cook eggs, in this part of the space, and this other object, golden retriever, in some other part of the space. Right? So I haven't told you yet anything about how to actually do this. But we want something that's able to place objects in space like this. The second thing is that we'd like to learn to place similar objects close together. Right? So not only do we want a model that's able to sort of position items in this space, but we want it to be the case that the question, how to cook eggs, and the phrase poached egg, even though not all the words are the same, the intents are related, and so we like them to be close together in space. Similarly, dog and golden retriever, like those are pretty similar, so we want them to be close together. And it would be really nice if an image of a poached egg and an image of a golden retriever like appear close to the sort of descriptive phrases of them, right? Okay, and then the third piece is we have to be able to retrieve neighboring objects really fast. So in order to actually use something like this to do search, we have to be able to take some new query or question. Maybe someone types in boiling eggs. And we need to be able to very quickly locate that thing in this space and find all the neighbors that are very close to it. And that may include the image and these other phrases or questions close by, and return them to the user, right? Okay, so those are the three pieces that are essential to being able to do continuous retrieval. By the way, sort of just to be a little more concrete, in our Quora case, well, I put this image, I couldn't find a sort of existing representation of questions on Quora, but this represents sort of questions on Reddit, so that's close enough. So here's this big cloud of questions that people ask in different topics on Reddit, and I don't know, the goal of the image was to show that, kind of similar questions end up getting clustered together. So you've got a music section and a fitness section and so on. Okay, so with Quora, we would take our 10 million questions and place them in some learned space, such that similar questions are close together. And then, given a new question, we'd encode it in the learned space, and we'd find the nearest neighbors and retrieve them. So I just repeated what I just said, but with this picture next to it. All right, let's go on. Okay, so the outline for the rest of the talk is that I'm basically going to talk about each one of these three components in some detail. So, okay, so first, learning to represent objects as continuous vectors. I guess I'm not going to just repeat all these things because I've said them already. Any questions before I go on? Yeah.
That's basically just kind of the plain vanilla search engine, but the value of the search engine comes with a grammar, search grammar, right? And so in some ways, addressing that part, you always say this and that, or this like that, and so on. That, in fact, presumably that representation is probably going to do very interesting, different kind of queries.
Yeah, so you're making the point that actually I dramatically simplified how search works, which is a fair point. So it's true that the language of specifying queries is much more complex and allows you to compose different things, with sort of simple operators like and or. So you can require that you want certain words to be there and certain words not to be there, and that's true. But at the end of the day, you're still using this inverted index. You're still indexing documents by the terms they contain, and you're still, that places the same limitation on you that I'm going to try to solve by representing things in continuous space. Yeah. Okay.
especially with that 1998. So vector space representation is the original search engine statistical representation for search. It's what it's called before this format, vector space representation. And so inverted index is the representation to make it efficient. But the way statistical searches, if used by Jerry Salton and others, was done, was to represent documents as vectors and to do similarity search based on similarity of the vectors, which you can manipulate in various ways, including k-nearest neighbors to find closeness in space, k-means clustering to represent closeness. So
Right.
that is how reams of research papers have been written to do search, and that's in 1990. So
Yeah.
what's better now is the learning part, which does work better for reading things. There's a lot of issues with that. So I do want to say that I think there's a bit of a misrepresentation of the state of the art of how search has worked in the past.
Yeah, that's fair. I think that it's true. So yeah, so the idea of latent semantic indexing, I think, dates back even further, right? Like, yeah, I think there are like patents from the early 80s where like the idea of latent semantic indexing, like you're saying, is to represent arbitrary objects like documents in some fixed dimensional space, which is exactly what I'm talking about doing with neural networks. So that's true. I agree. There was all this research. I just mean that in large-scale search systems, I don't think anybody does it, right? So I'm not claiming that I've invented some sort of new paradigm for doing this. Yeah, I agree. This has been around for a long time. I'm more interested in sort of making it practical.
Okay, and to say, we kind of talk about the history of search and in a lecture and put up here and say this is how it's done. I find that a little concerning, that's all.
Okay, fair enough. All right. Okay, other questions? Yeah. Oh, not a question. Okay. Okay, so I want to talk about learning to represent objects as continuous vectors. I should say, originally when I was making these slides, I put a picture of the patent that was filed back in the 80s, and I had some discussion about LSA, but I decided I just didn't have enough time to talk about it. So.
Without LSA, just counts of the words in vectors, without even reducing the vector space. It doesn't even have to be as indirect as LSA, and just doing similarity of the documents in vector space is the starting point, I would say, without all of the dimensionality reduction of LSA.
Okay, yeah, that sounds pretty close to what I'm about to talk about. Okay, so this is probably going to be very familiar to some of you and probably not familiar to others, but anyway, ask me questions as I go. Okay, so let's talk about this. This is sort of totally different for a second. Let's talk about the language modeling problem. The language modeling problem is, given some context, can you predict the next word, right? So here's a really simple example. And let's say that my vocabulary just includes 5 words, right? In reality, you might have 50,000 or 100,000 words in your vocabulary, and that makes everything more complicated. So let's keep it really simple for now. Okay, so I'm going to try to frame this with logistic regression, which I think is probably familiar to many people. Okay, so what if we wanted to solve language modeling with a traditional logistic regression? This is going to look a little bit funny, but you would do something like this. You would say, okay, let's represent each word as a one-hot vector, right? So this is sort of like indicator, you have sort of an indicator for the presence or absence of each word in your vocabulary at each one of these 3 positions, right? So in the previous word position where the word poach is, that's a one-hot vector, right? There's one of these 5 words in our vocabulary is present, so there's 1, and the rest are not present, so there's zeros, right? And you could say the same thing about the word to and the word how, right? And then you might concatenate those to get a representation with 15 numbers, 15 features of the context, right? So this is like 15-dimensional representation of the context, okay? And we want to use these 15 features to predict what the next word is going to be. So what does that look like? This is kind of a funny-looking logistic regression. But this is like a multinomial logistic regression, or sometimes called softmax regression. And so there are 5 possible words, each word in a vocabulary, that we'd like to predict, for which we'd like to predict the probability, right? And on the right there, that's sort of, I guess I can use my mouse to point. So this represents sort of the model parameters, right? So for each of these columns, you can think of as representing one of the words in our vocabulary, right? And so in logistic regression, you take your feature vector, which is those 15 dimensions, and you multiply it by these sort of learned parameters for each word, right? Each word in our vocabulary. And that gives us some score, some scalar value for each word. So the word chicken has some score, and the word eggs has some score, and so on. And then we apply the usual normalization, which is that little function there, where we exponentiate each score, and then in the denominator, we have the sort of total sum of all the exponentiated scores, and then we get a probability distribution. And so let's say our model then predicts sort of this picture of the probability distribution, where eggs has some reasonably high probability, chicken, because you can also poach chicken, and the other words have some low probability, right? Okay, so does that look okay? Okay. Okay, now let's do the same thing with word embeddings. Okay, so this is probably something you've heard of. This is something that I believe was, I think I can say, was invented fairly recently, like around in the last 10 years anyway, right? And it's come to have like incredible importance in natural language processing, and also in some other areas too. And it's really a simple idea. The idea is, instead of using a one-hot vector to represent each word, let's just arbitrarily create some two-dimensional representation for each word, right? So instead of having this one-hot vector with, you know, a bunch of zeros and 1, 1 for each word, let's say every word has 2 parameters that describe it. And we're going to learn those as well. And those are going to be sort of latent in the model. And so now I'm going to add 2 parameters to the set of all the parameters in the model for each word. So chicken has these 2 parameters, eggs has these 2 parameters, and so on. And the first step is, instead of creating the one-hot vector, I just go to my embeddings table and I look up the current value of the embeddings and I write them down, right? So each of these 3 words in the context has some value for its embeddings. Then I'll concatenate them just like I did before. And then everything looks the same, right? So now the features that are going into my model, before I had 15, now I happen to have 6. These are sort of arbitrary numbers. And now I do the same thing, right? It's still a logistic regression. It's just that now the features, rather than being fixed, are learned, right? And we can learn them using backpropagation. So it's sort of an extension of the kind of gradient descent you would use to train your logistic regression model. You can learn them now in 2 steps. First, you estimate the updates to the model parameters in the logistic regression layer, and then you update the parameters in the embeddings layer, right? Okay, so here's a little picture I tried to draw of what that training looks like, right? So in the previous picture, I was asking the model to make a prediction about the next word, right? During training, you're saying, I have a lot of examples of sequences of words, and I want to use that training data to estimate these model parameters, right? So in training, I actually know the identity of the next word, right? And for a second, I hide it from the model, and I ask the model to make its predictions, and that's what these guys are. And then I say, well, actually, I knew the next word was eggs all along. So that sort of looks like this distribution, right? It's a distribution with a 1 and a bunch of zeros. And then I compare these 2 distributions using a metric, in this case, cross-entropy, right? So I compare these 2 distributions, and I observe, like, okay, these distributions are not exactly the same. I'd like to update all the parameters of my model so that next time around, if I were to see this exact same example, I'd come a little bit closer to predicting the true distribution, right? So this isn't an animation, but you can kind of see if I go back and forth, something like this happens, right? The value of the cross entropy is sort of propagated back down through the model. I make small updates to all of the parameters so that next time around, I get a little bit more confident about eggs, right? Any questions?
What's special about 2 dimensions for the embedding, or is that just to keep the diagram simple?
That's to keep the diagram simple. But in practice, people do not use 2 dimensions. People use usually something like 100 to 1,000. You could ask, like, well, what do these dimensions represent, right? We've sort of obfuscated things in the model, right? Like, often you use a logistic regression so that you can sort of say something concrete about how important each factor is. And what I'm doing is I'm saying, well, actually, I'm going to represent poach with 100 numbers. And, when I do that, I exert no control over what each one of these dimensions is going to represent. And I will let the model decide during training what they mean. And some of them may end up with some interpretable meaning, and some may not. Yeah?
How would we pick the dimensionality of the embeddable space, embedding space?
Yeah, good question. People usually just like choose something.
They just go for it.
Yeah. I mean, this is like a hyperparameter of the model, right? So this is the kind of thing that people often, there's sort of trade-offs associated with these things, right? Like, going from 100 to 200 dimensions, for the task that you're trying to do, if you really care about language modeling, increasing the dimensionality might give you better performance, but it might slow things down or,
How do you check that the dimensionality of the embedding space is accurate? Do you have some test case with a number of queries that you figure out that the embeddings capture the relationship experience with, or what's
Yeah. Yeah, that's a good question. I've got some pictures. So people have thought a lot about how you might evaluate the quality of an embedding, right? And actually, for the purposes of this talk, I'm not that interested in the embeddings themselves. I'm interested in something else. But it's worth talking about for a second. So one thing that people have observed is that the embedding dimensions are meaningful in some respect. One way to show that is to look at the nearest neighbors of certain words, right? And one thing I have to explain is that usually people don't use 2 dimensions, right? They use like 100 or 500 dimensions, and then you need to like project that down to just a couple dimensions, and they do this sort of fancy nonlinear projection so that nearest neighbors are preserved. That's what that TSNE thing is. Anyway, if you then project all the words in your vocabulary into some big space, you can zoom in on that space and you observe some kind of neat things. Like, look, all these number-related things are really close together. And even if, you have numbers spelled out, like 5 and 6, or you have numbers, in decimal format, like 10 and 20, and here's half. And the model has learned that all these things go close together. And also these sort of number-related words, like some and many, those end up in the sort of generally same space. Also on the right, you have all these sort of related words like leader and president and chairman and so on. So one thing you can do is sort of examine the space, just sort of confirm that indeed things that are similar appear close together. Another thing that people like to do is look at these sort of analogy-like relationships, right? And you can ask, these are like SAT analogies, like France is to Paris as Italy is to blank. And then you ask the model if it can solve the analogy, right? And the way you do that is, well, you can draw here, look at this example up here. If you observe that man is embedded by some point in this space, and woman is embedded by some other point, and you can then draw the vector that connects them, and then you can apply that same vector to uncle and see where you end up. Like, what is the nearest thing to uncle along that vector? And it turns out that indeed the word aunt is very close, right? So that's sort of the model solving this analogy. And you can ask, how often does it solve the analogies? And so here's some examples, like that the model is getting close to right? Like France is to Paris as Italy is to Rome, and so on. Big is to bigger, as small as to larger, cold is to colder. You got some interesting things like Einstein was a scientist, and Messi is a midfielder, and so on. I think if you look closely, you can find some mistakes the model makes, like here Berlusconi is to Silvio as Putin is to Medvedev. Well, not quite right, but not too bad. Okay, I'm going to move on to the next part, unless you have some questions. Okay, so that's sort of a primer on the idea of embedding. So the next part is about learning to place similar objects close together. Okay, so the history of NLP involves a lot of training models from small labeled data sets. So one thing that I and many people that I know have done, spend a lot of time working on, is something like the parsing problem. Like, given a sentence, can you train a machine to diagram it like this, right? To break it down into like the verb phrase and the noun phrase and where the prepositional phrase is. And over time, we've made a lot of progress with this. But it's hard to find labeled sentences, like sentences labeled with parse trees, right? And so what we've done over time is like pay highly trained experts to annotate some of them. So like we took a corpus of the Wall Street, well, I'm saying we, but obviously it was not me. So there's an annotated corpus in the Wall Street Journal, like of 1 million words. So, I don't know, 20 years ago that was a pretty big size, but these days that's quite small. So 1 million words annotated with parse structures. And you can take that data and try to learn these algorithms for being able to improve translation by somehow like training a parser and inserting it in the right place into the translation model. And a lot of people spent a lot of time doing this with very limited success. Like it was very hard to get even the best parser to make any difference to a translation system. And part of the problem is just that the translation system is trained on so much more data that it sort of is able to learn what it needs to know about these sort of subcomponents like parsing. Okay. All right, I don't think I want to say anything else about it. Okay, so I'm going to tell you about this model that I'm going to call the dual encoder model. And the dual encoder model, I guess one last thing to say about translation is like a generative task. It's like, given a sentence in English, can you generate text in French? What I'm concerned about is this retrieval problem. So it's actually not generative. I just want to place objects close together in space. So it's a little bit different. Okay, so here's a like overview schematic of this thing I'm calling a dual encoder model. So the idea is that an encoder is something that represents an arbitrary object as a fixed dimensional vector, right? So I just told you how to represent words as fixed dimensional vectors. Let's like scale that up to representing whole sentences or maybe images as fixed dimensional vectors, right? So the encoder is like one of those things in the blue box. And the dual encoder takes two fixed dimensional vectors produced by two possibly different encoders and tries to put similar ones in the same space, right? And I'll try to describe how that works in a second. Here's a sort of zoom-in view on what a sample encoder neural network might look like. So looks sort of similar to before, where maybe you take each of your words, you represent each word with a two-dimensional embedding. Then you sort of, at the next layer, you combine the embeddings. Maybe you average them. That's sort of a standard thing that people do. And then you can add sort of arbitrary hidden layers that sort of add extra computation on top. All these arrows sort of are indicating that like this node right here is like a combination of, is some learned combination of what's at the previous layer, right? So there are all kinds of different possible encoder neural networks, and I'm not going to spend more time talking about them. The important point is that it's some neural network that generates a fixed dimensional representation of an object. So here's an example for text. The sort of analogous thing for images. Oh, sorry, question.
Just what the backdrop is against. Like, what's your clue? You want to learn how to follow this?
I'll talk about it soon, I promise. You could imagine something similar for images. I'm not going to describe it now. It involves convolutional neural networks, which basically is like sliding this little window over regions of the image and extracting features. And you can use that to also get a fixed dimensional representation. So let's set that aside for now. But here's like a schematic for the dual encoder that would place text and images close together, right? So here you have your question encoder and your image encoder. Each produces a fixed dimensional representation, and then you have your similarity function that says like how similar these two objects are. Okay, so now I have to back up for a second and tell you about this this idea called the sampled softmax. This is like this sort of like a one weird trick thing for machine learning. So let me back up to the language modeling case. So this is the picture that I showed you before, where we have the truth distribution that comes from the label, like the actual next word, which was eggs, and the predicted distribution that comes from the model. And then we compare these two before we do backpropagation. Now, in order to get this predicted distribution, remember, we need to compute a value using the model parameters for every single word in our vocabulary. So that was no big deal when we had 5 words in our vocabulary. But if we have 100,000 or 1,000,000 words in our vocabulary, then every time we want to make a prediction, we have to compute, we have to do a lot of computation. We have to compute this scalar, which people call a logit, that represents each individual word in the vocabulary, and then do this normalization, and then you get your distribution. That's a lot of computation. And so the sampled softmax trick is to say, okay, let's instead compute the prediction for the correct label. This is during training. Let's compute the prediction for the correct label, because that's important. We want to know what the model thinks is the probability of eggs. And let's compute the predictions for some random word. So let's choose like 1,000 random words. So like 1% or 1/10 of 1% of the words in the vocabulary. And we'll estimate the softmax distribution given that random sample. And everything else we'll say, well, it's just a 0. And then we can still compare these two distributions sort of in an inexact way. And it turns out that's good enough. And you can then train a language model much faster, like many orders of magnitude faster. And so that's led to a lot of improvements in language modeling. But I'm going to exploit this in a much more important way to answer the question that you just asked, for how to train the dual encoder model. So now, instead of predicting the next word, I want to predict the similarity between sentence 1 and sentence 2, or question 1 and question 2, right? So in this example, I have this, on one side I have how to poach eggs. On the other side I have poached eggs recipe, or I forget what my example was. Let's say it's poached eggs recipe, right? So I have these two examples, and I want them to be close together, right? So I have this positive pair, and I want these two things to be close together. And that's sort of all I know. But let's say I have some very large database of all kinds of other sentences or other questions. Like in Quora, there's 10 million questions. And so I will make the assumption that if I sample a few of them at random, they're sort of negative examples, right? If I sample some random negative, like where is Fiji, the chances are that that's not synonymous with how to poach eggs, right? And so this is like the sampled softmax trick applied to dual encoders, right? Yeah. Yeah, that's a good question. So I haven't told you yet where to get training data for this. All I've said so far is assume you have positive pairs, right? So let me come back and we'll talk about training data a little bit later. But my assumption is that you can get lots of these positive pairs. And then once you have positive pairs, you can use this sampled softmax trick to find random negatives that sort of stand in for the whole world of possible negatives. Now, in this case, the sampled softmax is crucially important because we can never enumerate all the possible sentences that are negative examples. Like with our language modeling case, there was some fixed vocabulary. And so we could enumerate all the examples, but here we can never enumerate them, so sampled softmax is even more important. Okay. By the way, here's sort of an alternate model architecture. So another way, this is a bit of a non sequitur, but it's important. So another neural network architecture for predicting the similarity between two questions is something like this. So maybe you can see the difference between this and what I showed before. I can back up if you'd like. So here I have these two inputs. Then I do the embedding. I get some, sorry, I shouldn't say embedding lookup, but I produce, or I guess I could. I produce some embedding for the words on either side. Then I do a sort of combined embedding, like I concatenate the representation of sentence 1 and sentence 2. And then I have some like arbitrary hidden layers, some like extra neural net computation on top. And eventually, it's a regression problem, and I want to predict how similar these two things are. So there's this diagram, and then on the other hand, there's, well, I don't have a great picture, but a diagram like this where there's sort of two separate towers, right? And why is this an important distinction? Well, remember that I want to use these models to do retrieval, right? Which means that I need to use the model to create a fixed, like a static representation of everything in my data set. So if I have my 10 million Quora questions, I need to use the model to represent all 10 million of them and have them just sit there. The problem with a model like this is that I'm required to see both the left and right side to make the prediction. And then it becomes very expensive to do retrieval, right? Because then I need to compare my current query with every single thing in that 10 million database, right? But the other model architecture where I have these two separate towers that are only connected by a distance, that allows me to index all of the items in my data set and then use nearest neighbors to find the things that are closest, okay? Okay, by the way, sort of maybe not necessary to talk about, but it turns out that you can kind of compose these things together and train them all together. So, I told you maybe you have some data set of similar questions, right? But maybe I have a data set of, matched questions and images, or maybe I have a data set of matched questions and documents. That's starting to sound a little bit like what Google web search has, right? It turns out that you can train all of these things together, all these encoders together in a way that sort of improves all of them. And the resulting, what ends up happening is that in that way, we're able to encode all these objects in the same space, right? Sort of force all these objects to end up in the same space by training all these things together. By the way, I threw in some sort of interesting retrieval examples. So these are some examples that I noticed from Quora where there's very little word overlap, right? So the model is able, given this phrase on the left, what does diatonic semitone mean in music? It retrieves what is a half step called. So it's not a perfect sort of one-to-one correspondence between those things, as maybe my brother would tell you, but they're pretty similar, and it's cool because they don't share any common words, right? Or what is the average price for portable toilet rental, and how much are porta potties, right? So again, very little overlap, or how to increase your cerebral capacity, how to grow mind power. So it's able to do this kind of cool thing where not only can we place words with similar meaning close together, but we can place whole sentences with similar meaning close together. So that's kind of cool. Okay, questions about that? All right. I want to talk briefly about this last step, just because it's sort of the last thing that's important to make this all work, although this is not really something that I work on personally. Okay, so this is the problem of finding nearest neighbors. And you can imagine if you've got these 10 million Quora sentences, and they're all embedded in a 100-dimensional space, that's like this really complex space. And then I'm coming along with a new question, and I want to embed it, and I want to find it in that space. I need to be able to do that fast enough that search is actually viable, right? So people tend to call this problem locality-sensitive hashing. I guess that's sort of the name for the solution. And it's a form of approximate nearest neighbor search where you create these hash codes that correspond to little areas so that you can quickly retrieve the hash code for a new object and then quickly go look up what else is in that area, just like a zip code, right? So yeah, so I guess I just said this. So it's sort of like constructing a zip code system from scratch where you don't know the map, right? But it's sort of analogous, right? Like in the zip coding system, each of these general areas, like the first thing we do is we do this partitioning with the first digit of the zip code, right? Like the whole West Coast is like the 9 zip code. New England is like the 0 zip code. And so each successive digit of the hash code refines the area, right? Until in this picture, like you get down to these very local areas. So if someone says like, oh, this object is 94704, that tells you a lot about the object because now you know it's like basically on Berkeley campus. Okay, and I guess the last thing I want to say is like does it work? And actually, yes, it works very well. Sort of surprisingly to me, because I hadn't played around with this before. But it is a sort of area of active research, like scaling up to like many billions of candidates. Like sometimes you have more than can fit on one machine, and so you need to do this in a distributed way. Like basically, if you want to do real search, you're going to need to do this on like a very large scale. Yeah.
So, it's a funny thing that, you started your argument saying, well, basically when we were presented with words, you basically have to have this reverse index for basically looking up for which given word, which other document has that word, right? Which effectively becomes a code. And then you say, well, by now we actually go and represent these things with these continuous vectors, which is great, it has all these benefits. But then when it comes to retrieval, you go back to representing this code, and effectively you go to a version of like the reverse index. So in some ways,
Yeah. Yeah, that's a good point. I hadn't thought about that way of putting it. But yeah, so I agree, there is some similarity. But yet, what you might end up with could be quite different, right? Because of the way that things are represented. And well, I don't know. Here, in this little plot here, I did the follow. Let me describe this experiment. I don't think it's going to answer your question, but I'll describe the experiment anyway. So here, I wanted to know how much does this LSH, the locality sensitive hashing, diverge from exact search, right? So if I'm willing to spend the time, I can compute the exact distance between my query and every single thing in the data set, as long as the data set's not prohibitively big, right? And so I said, okay, let me choose a bunch of different sized data sets, like 100,000 objects, a million, well, I guess in my example, up to 1 million objects. And so that's a reasonably small, like it's a big enough number that retrieval is important, but it's small enough that I could do brute force comparison, where I take each guy and compare it to every single thing in the data set. And then I'm comparing, I want to compare this exact search to what I get with locality sensitive hashing. And you might expect that as the number of candidates grows, the divergence would grow. But actually, that wasn't the case. It turned out that actually, as the number of candidates increased, the divergence actually looked like it's either flat or sort of decreasing. So I was that caused me to be impressed with these sort of hashing techniques and their ability to find like this sort of needle in a haystack problem, right? Finding the things which are close in this semantic space. One thing to add is that often the way LSH often works is you might use the hashing to find all of the sort of nearest neighbors in some small circle, right? Or some small sphere. And then you might still compute sort of one-to-one comparisons within that little area to sort of get a more precise ranking, right?
right, it goes to a second stage ranking. But in some ways, whenever you were saying about the reverse index, like Mario was talking about, basically saying, well, there's more to it though, because most of the time, even if I give actually
Right.
the stage right now, the first step that will give you ranking. From then on, you can go to a second stage, which is basically applying more carefully. But normally we do that also in search engines.
Right. Yeah, I think the place where this kind of technique can give the most benefit is improving recall, right? Like things that you wouldn't have been able to find. I mean, I don't mean to suggest that search doesn't work well. Like it works great. Yeah. But yeah, no, I think that it can improve recall. Like I think that, for example, in the sort of long tail of stuff on the web, search engines tend to, partly as a result of the inverted index, tend to be biased towards the head. And this might be a way to expose things that are more relevant in the tail. I'm not 100% sure, but that's, that makes sense to me. Yeah.
Yeah, it seems to be a lot of the innovation is on the hashing part of the retrieval here, because you said at the beginning, well, search engines didn't use vector space model. Well, TF-IDF is very established in a vector space model, but in practical systems, doing k-nearest neighbors or k-means wasn't practical. I think because a lot of these innovations weren't scaling yet.
Right.
So it seems like a lot of the advances really had to be on the system side to make that stuff scale.
Yeah.
But I will say that, and you're using cosine and all that, which is the classic information retrieval vector space model approach.
Mm-hmm.
But what never worked was the vocabulary problem was not solved, and which is the examples you gave where the words don't overlap
Right.
and short queries, and that's where embeddings and the ONet technology has driven the important advance that work way better than LSA and previous methods did.
Right.
So my question was, how would these methods work for long documents, for long queries, for matching against long documents?
Yeah, I don't know. So I haven't worked on the document retrieval problem. I think there are people at Google who are thinking about this, but it's early. So one issue with long documents is that they're long, and the models that we tend to train for text usually operate, like for translation, you know, we don't do translation at a large scale. Like we do translation one sentence at a time because it breaks down if we try to use the same sorts of models. You know, we try to use an LSTM over like 1,000 words and it stops working. So we don't have good models, I think, for sort of dealing with longer pieces of text. I think this will be a big area of research. Like I think it's exciting. I think you might need sort of a more structured representation of what's in a document. Also, one of my assumptions in this whole talk was like, you're going to create a fixed dimensional representation of all the objects. And that might break down when it comes to document search because, you know, lots of very different queries can resolve to the same document. Like the Wikipedia article for Barack Obama, like that responds accurately to a huge variety of queries. And so to say that we have to represent it by one fixed dimensional vector seems like too much of a shortcoming. So what's the right approach? Like I don't know what the right approach is. So I think it'll be a while before this is actually used to represent whole documents. I think what will happen first is we'll find ways to represent answers and do question answering better. So one thing I'm interested in is, well, okay, I can represent all these different objects in the same space. Let's index lots of sentences and see if I can do question answering by finding the sentence that's closest to the question that you asked, by placing, you know, having a question encoder and an answer encoder. And then, you know, we don't necessarily have to encode like whole documents, but just sentences. So anyway, I don't know the answer to your question, but. Yeah, that's right. That's right. Right. I think we've also trained ourselves to search using keywords. Like over the last 20 years, we've evolved with Google to like learn how to issue queries that are likely to get the information that we want. And so we've created this query language that's sort of like this new thing. I don't know, Google goes to, by doing stuff like suggest, they try to get you to like ask it questions in natural language. But there's all these cases where because the search system doesn't understand the way words compose together, like it's often hard to find what you're looking for if it's a little bit more complicated, right? Like, a famous one that I've seen is like Macintosh controlled infrared remote, right? So that's like this series of 4 complicated nouns. And so Macintosh controlled infrared remote, like that is a phrase that indicates that you're looking for software that can control your TV, right? But if you search for that on Google, you're going to get a bunch of remotes, like not software, right? So Google doesn't understand how all those words like compose together when it's doing keyword search. So this kind of like neural retrieval at least has the opportunity to like learn how to compose stuff together and then represent it in the right part of the space. Okay, I only have a few more slides. Okay, I wanted to just sort of mention a few sort of high-level things. So about what this kind of retrieval could mean. So one thing this could allow is retrieval across languages. Like right now, every retrieval system that I know of is language specific. You search in English, you get stuff in English. You search in Spanish, you get stuff in Spanish. But we can train models that embed all languages in a shared space, right? In fact, I've done experiments like this. This is something that's like always excited me about language processing and always seemed far away. And now it's like actually here. And this is a picture from, actually from translation. Yeah, question?
This is really provocative. I'm wondering if you think that, of course there are semantic relationships that work across languages. Do you think that there are any semantic relationships that might be language specific, such that there is no interlingua between them?
Yeah, sure. I mean, there are words with no translations in other languages, but there are words, but you could always sort of summarize the meaning with enough words, right? So as long as we're not limiting ourselves to like, one word to one other word, a model like this might be able to embed some word with no English translation with an English phrase that roughly means the same thing. You can always do nearest neighbor search and find, for this Russian word or this Russian phrase, what are the English phrases or words that are sort of closest? And there's no reason why we can't do that. And so, this can allow you to issue a query in English and ask for retrieval in any language. I was going to show you this. So this picture is actually from a translation paper, but the idea is the same. And so if you zoom in on this like little region right here, you see whole sentences like, I don't read Korean or Japanese, so actually it's not that exciting, but you can hopefully take the author of this picture's word for it that these are translations. And you see that like the translations for these 3 languages are sort of clustered very tightly together in this large space. And we can do the same thing with these dual encoder models. The other thing is that I already talked about is this also allows retrieval across modalities where we can do document or image or audio or video retrieval given a query. Like we don't need to constrain ourselves to keywords anymore. We can index all kinds of crazy things, right? You can, I was talking to my brother the other day about indexing. You could index audio clips or whole songs. I don't know the details of how this would work, but the general framework still applies. And then for an arbitrary query, you could find the nearest neighbors in that space, right? Like, I could ask like for the sound of like a bird chirping in South Hall, and maybe we'd find some audio recording, maybe not from South Hall, but I don't know, something close by. And so there's no reason why these sorts of models can't embed all kinds of different sorts of objects in the same space. I mentioned before this allows for learning complex relationships between objects, and then I was also arguing that this would increase retrieval in the long tail. I wanted to say quickly, one thing I didn't talk about, I think this is the last slide, yeah, was, well, who has this data? Like, what kind of data is necessary to do stuff like this, and who has access to it? And certainly Google's a good place to do this research because the search logs have all this data in it, right? Like, I can look in the search logs I can sort of exploit the fact that Google search works really well to get lots of examples of queries and documents that people clicked on, to connect queries and documents, or queries and images that people clicked on to connect those two modalities. I can look for pairs of similar queries or pairs of similar images. But actually, I think there are lots of creative ways to get really large data sets of positive pairs, like from public data. So I don't think that it's true. Like, it is true that Google has this really high quality data, but I think anyone could do this research effectively. So, like, one example I can think of is Reddit. So Reddit contains these like sort of forum-like threads, which are in the public domain, and there are questions and answers and then sort of more discussion below. And you can train one of these models to place sort of parent and child in the same space. And that sort of has the same effect as paraphrasing, right? If you can place a parent and a child in the same space, well, actually that's sort of a longer argument, but you can sort of think of it as question answering, right? Like, you can take a parent as like a question and a child as an answer, and you can train one of these dual encoder models with the same sort of techniques I described to place this text data in one space. And Reddit has, billions of pairs, so there's lots of data there. Yeah, I think there's other sources of data that are also in the public domain that you could sort of be creative to explore. Okay, so that's all I have. You can ask more questions if you want.
Thank you so much, Dan. I think we have time for several questions.
You may have already asked all your questions.
So I have a quick question. When you do this similarity measurement between two documents, your embeddings are the same size because you have the same number of words or something like that? It's like the embedding was two-dimensional for the words and then you sort of concatenated them. If they're not the same size, would you use an RNN for that part?
The only thing that I did was, let's see, what's a good picture?
This is a good picture.
Here the embeddings are concatenated, but let's see, I think in this model, this is an encoder that I said produces a fixed length representation. Here there's this averaging layer, and so this is going to be of the same size regardless of the number of words. So in this feed-forward model, this is a way to sort of factor out the number of words, right? Sure, you can use an RNN as well. People have found so far that they haven't been able to get much better performance out of RNNs, but yeah, there are all kinds of other models that you could sort of stick in place. I kind of put in the simplest thing I could think of here. And if you have lots of data, it turns out the simplest thing works quite well. Yeah.
So thank you very much. I really liked this framing of search as kind of, things that are close to each other in some space. New to me, maybe not new. I think that the one thing that sticks with me is this idea that the dimensionality of the embedding space is a hyperparameter. Do you think that there is any way to estimate an appropriate dimensionality empirically through some sort of corpus? I know that obviously we can't anticipate all searches, and often the value of search is that some of them are novel, but do you think that there's any method?
Yes, I think there's a method, and I think the method is sort of strictly practical, right? Like, typically in these models, there's something that you're trying to do, like retrieve stuff, and you'll create some evaluation set, and you can increase the number of embeddings until you don't see any improvement anymore. And that's the right method. But your question is interesting because it suggests somehow that there is a reasonable or right number of dimensions to represent sort of words, like vocabulary words or images or whatever it may be. And yeah, I think that sort of, I don't know how much I want to say about it, but like it represents some amount of bias that we have coming in, that like there is some sort of right amount of sort of dimensions, like features that we use to describe anything in the world. And
That's not what I'm saying. That's not what I'm saying, nor is it something I believe. And I think that what I'm saying is that with respect to any set or any distribution of queries, there's some set of dimensions that will satisfy stuff, basically. And is it possible to assemble that corpus beforehand and analyze it in some way that allows us to figure out the set of dimensions? I understand that, you know, there are always going to be some limitations and so on, but that there are biases in these algorithms regardless, right? There are going to be biases in these dimensions, if not in the way that they're represented, in the way they're selected by queries, right?
Yeah, well, I don't know of any way to, I'm a little bit confused about what you're asking, but the only way I know of to, the way I think about these embeddings is sort of as strictly functional, right? Like, I was just trying to say that it is true that if you then go and, after you've trained this model, you then go and inspect what each dimension represents, you might find some interesting correlations between what's in those, what's in dimension 7 and, some characteristic of words, right? Like you might find that dimension 7 sort of corresponds to like the gender of, pronouns, right? For example. But that may not be the case for all those dimensions, right? Sort of, anyway.
The dimensions looking for query.
Sure, yeah.
Two very quick questions. There is a long history of interlingual research, and there's Marty's thesis grandfather, Roger Schank. There's people like Sergei Nierenberg around the same time, which is a more sophisticated one. First of all, have you looked at any of this stuff?
Only insofar as it was mentioned to me when I learned about translation in graduate school. But I don't know much. Yeah, could maybe tell me more.
Well, no, I'm asking the questions and you're
okay.
answering. I don't. Okay, no, you have answered. So
I don't know about
the second question is more this where the use of this word neural, for example, there's some of the top minds in neuroscience are meeting up in Simon's Hall these few days, trying to work out what the basic algorithms the brain uses are, and what do you think the basic algorithms the brain uses are? When you use that word neural, what do you mean?
When I use the word neural, I'm only using it sort of because of the convention of referring to like these kinds of things as neural networks. Like, I think in my head there are some sort of loose association between what this is and maybe what we know about what happens in our brains, but it's not specific for me. Like, I'm just sort of using it as a descriptor. I don't know, do you want me to say a little more about the sort of association that I understand?
If you'd like to, sure.
Okay. Yeah, so I think one crucial part of neural networks, sort of in the machine learning setting, is the idea of nonlinearities. So actually, I sort of left out this discussion from my description of this picture, but like what's happening here at this, often we refer to this as a neuron, right? It takes input from these two guys, right? And this value is like a linear combination of whatever's here and whatever's here. So this thing times some learned parameter plus this thing times some learned parameter gives you this. And then what comes out of there is like you apply this nonlinear function. And the nonlinear function is designed, I don't want to say it's like, I mean, it's sort of inspired by what happens in your brain, where like a neuron receives sort of stimulus input from other neurons, and then nothing happens up to a certain point, at which point it fires and sort of sends its information on to the next neurons, right? And so there's this like loose analogy where, you know, that neuron sort of fires its information off, like it's like representing a 0 up until it receives some sort of, gets to some threshold of input, at which point it sends its information up to the next layer. And that nonlinearity, like that threshold, is really important to getting neural networks to work in practice. And I think that's something that's sort of parallel in brains.
We have time for, I think, one more question. So one or two.
Thank you. So I'm curious, I'd like to know what happens if I ask an ambiguous question to your system. And I've been like racking my brain to try to think of a clever ambiguous question. The best I could come up with is, where can I buy a Jaguar? So presumably, it's terrible.
Orange juice machine. Where can I buy orange juice machine?
Okay. So actually, the Jaguar is a little bit easier for me to talk about. Sorry. Thank you, Marty. Marty tried to rescue me, but so the reason is, I would imagine that questions about cars will be mapped to sort of one region of this representation space, and questions about cats will be mapped to a very different kind. And because this is a metric space, either way that, any way that my question is embedded, it can't be close to both of those. So I'm wondering what happens.
Yeah, good question. So the same problem happens when you're training just plain word embeddings, right? Forget about complex sentences, like the word Jaguar itself is ambiguous, right? And so when you're training your language model, like, does Jaguar end up close to the cats or does it end up close to the cars? What's that?
How fast does Jaguar go?
Anyway, I'm just trying to create an even simpler version of your question. It's true, this is sort of a shortcoming of the way that people think about word embeddings. Like, every embedding has, every word embedding has sort of exactly one point in space that's representing it, one fixed set of parameters. And what you end up getting is just reflective of what's in the data. So if your data is coming from news and there's lots more car Jaguars, you know, your embedding for Jaguar is just going to be closer to the cars. Similarly, in a model like this, you get the same thing. It's sort of whatever the data shows. I guess a couple other things to say about it. One is, when you embed whole sentences rather than individual words, there's some hope that the rest of the sentence can disambiguate it, right? And so the more context you have, the more sort of disambiguation the model could do. Sure, in your case, in your example, like, maybe we can't do disambiguation and then you sort of get whatever the majority class is, but the longer the input, and you know, there's also opportunity for models like this to take additional inputs. So maybe when we're indexing possible answers, we'd also like to include some context information about the document in which we saw that answer. And that document could help to disambiguate, sort of decide whether this is a sort of Jaguar that appears near the cats or the cars.
There's also one point, which is in a 1,000-dimensional space, you can probably be close to both. So, you know, it is because of the high dimensionality that allows you to actually be close to both and still be able to actually, you know, do something.
Well,
But you want, how, you specifically want, where can I buy a cat, or how fast does a cat go, to be far from where, how fast does a car go?
Not necessarily. Because a cognitive model is required of those concepts anyway when you ask a question like that. So maybe you do want to.
there is some work on, I mean, there are possible solutions to this problem. It's not we don't have to throw up our hands. Like, you could, you know, decide that, for example, with your word embeddings, you might decide like, okay, words have different senses, so I'm going to make multiple copies of each word embedding, and I'll allow them to move sort of to different parts of the space. And people have done some research like that. So there are possible solutions.
Okay, Dan Gillick has our last question.
Oh, I'm David.
I mean, David, sorry. David Bannon. Looking at here.
Yes. So thanks Dan so much for a great talk. So my question is kind of related to Paul's, but I want to sort of think it through from the perspective of the training data and the implications that the training data have for the kinds of similarities that you're learning. And to take the example of search engines, I mean, there's a lot of different kinds of information-seeking behavior that people use when they go to a search engine. A lot of different kinds of strategies they use when they issue queries. So some of it, some of it is this classical: you search for a question, you want an answer. You search for a string, you want to have some information about that string. Sometimes it's just typing in Twitter into Google, so you can click on that first link rather than typing in twitter.com. Sometimes it's just foraging, where you want to know something about Fiji, so you type in Fiji and just see where you go. I'm curious to have you talk just about where real training data comes for learning similarity for these kind of query models, and how the choice of where that training data comes from can influence whether or not you're privileging or biasing these kinds of similarities toward one of these methods of information-seeking behavior. How, in short, I mean, sort of generally, how does the training data influence the representations that you're learning as a function of the data?
Yeah, yeah, good question. I'm not sure I can give a good answer. At Google, the training data is mostly going to come from the search logs. And that definitely means that there's a bias, and the bias is towards the way Google search works today. So there's this interesting kind of interaction between we want to train a model that could in principle replace or improve on Google search, but we're sort of limited to data that we can draw from Google search. So and I'm not sure quite how that influences what we end up getting, but one thing that's interesting about these models is that, and so to be a little more concrete, I'm making this claim that one nice thing about these models is that we can retrieve from the long tail, right? You ask some complex question about restringing rare guitars, and I surface this forum buried in some Reddit thread from 10 years ago where people are talking about this. Google doesn't work that way today, but in my mind, it could. And, but how are we ever going to get there if I'm training off of this click data where people only ever click on one of the top 10 results? I think there is a little bit of hope because the amount of logs data is huge. It's really big. And the number of parameters in the model is by comparison small. So because of that bottleneck, if we can figure out how to actually leverage a huge amount of training data, with a relatively small number of parameters, we can potentially force the model to generalize well enough, I think, to do the kind of thing that I just suggested. But I think it's a hard problem. I'm not sure how difficult it will be.